Hi guys, my name is Chitrika, and I'm here to present on how Wav2Vec capabilities are combined with single generative model. The topic for today's our presentation are self-supervised learning, autoregressive models, lag, contrastive predictive coding, and Wav2Vec architecture, and the transformer with detailed explanation of encoder-decoder, GPT-3, current ASR model implementation, Fourier transform, and we will go deep into the architecture part of Whisper as well. And finally, we'll talk about the Pragna and multilingual approach that we are trying towards implementing Pragna. So, starting with the self-supervised learning, it is a machine learning technique that will leverage unsupervised learning method and for the task and typically requires supervised learning methods as well. Instead of depending on labels data set for guidance, self-supervised learning creates implicit labels from unstructured data. So, if in self-supervised learning, the task is divided into two parts. One is pre-test task and one is downstream task. So the pretest task will involve using self-supervised learning AI system to learn meaningful representation and from unstructured data, and the downstream task will involve utilizing these meaningful information, so that it can be typically handled for supervised learning. So autoregressive model is basically like a linear regression model. It works like a linear regression model itself, but only the difference is that in autoregressive model we use independent variables which are relying solely on the past regressive predictive values, and this is the formula of the autoregressive model, and it can be like simplified in this way, where the y represents the predicted outcome based on multiple previous results, and each multiplied with a coefficient 5, and these coefficient represents weights or parameters that determine or influence of each predictor onto the new results. The formula also accounts for some random noise, that is error term, and this error term will can be improved further for the improvement of the model. Now coming to lag, lag is basically like to improve the accuracy of the autoregressive model. We can like increase the number of the lagged values, that is t, so that more numbers of past data points can be like included, so that the predictive capabilities can be enhanced. And the challenges that we face during the self-supervised learning called contrastive predictive coding is that firstly the error terms like mean square error and cross entropy is not quite valid, because a signal can lose its local smoothness for a high dimensional data. So if we try to model it in this way, that is probability of x given c, which is a conditional probability, where my x is the target variable and c is the context variable. So directly, this may not be much optimal for extracting the maximum shared information between x and c. So we use this kind of a formula here, so that we divide it based on the entire probability, of instead of just using the conditional probability, so that it can get the maximum information of mutual information between the context and the target variables. This is the architecture of contrastive predictive coding, where we have nonlinear encoders as GENCs, and these are the input variables over time based on audio, and this encoders, it will convert these input variables into a latent representations. So that is the dot product of this encoder and the input variable, which gives these latent representations. And finally, for time which is less than the like t, that is again converted into latent representation using the autoregressive model, as I discussed before. So these latent representation totally like all of these latent representation help in the next prediction. So The in contrast to predictive coding as well, as I explained before, that we cannot use directly the conditional probability. So the probability density function is directly proportional to the formula that was previously formulated. So when we normalize this, we get this particular equation where my WKT, this is the transpose term, and this is the like contextual term. It's a linear transformation used for prediction, and the major term is this ZT, which is the latent representation, and CT, which is the latent representation for less than time. So these two representations incorporate all the additional information from past for which is useful for prediction. So now we will go to the Wav2Vec architecture and how it is trained. So it basically takes raw audio as input and then converts that into some latent representations, and it is trained on the like Wall Street Journal, Libri speech, and two sets of Libri speech data. One is for full training and one is for clean data, and it is comprised of fully convolutional layers and consists of two types of networks, encoder and context networks. So before understanding these two networks, we would understand the latent space. So the latent space refers to the representation of the space where two similar kind of like vectors are placed in the same position close to each other. So for example, in context of word embedding, similar kind of words with same meanings are located close to each other. And in case of audio, like waveforms having same pitch, same speaker identity, they are placed closer to each other for representation. So now we come to the encoder network. So this encoder network will uh, basically it will generate the lower dimension from the latent representation and for future prediction, and then this lower dimensional data is passed to the context network. Why we require lower dimensional data? Because um, instead of predicting the future prediction from the raw audio, the audio might contain a lot of noise. So those noise needs to be removed so that the meaningful and stable data is used only for the next predictions. The context network works like as we know that there are certain latent representations of the input. So this latent representation is further passed into the nine convolutional layer stacks, and then after it produces some contextual representations, which is present in the receptive field. And this G is basically the context network, and V denotes the receptive field, and all of these are the outputs of the convolutional layer that is obtained. So the architecture looks somewhat like this, where we have X as an input, and this is the audio. So X is the representation of the audio as an input, and then there are convolutional layers. Then we get the Z as latent representations, and then again convolutional layers, and then we get the contextual representation. These L1, L2, and L3, these are the 512 channels which is present in between the convolutional layers, and it includes the normalization layers like ReLU. And Wav2Vec architecture is almost similar to the contrastive predictive coding. The only difference is that it is fully convolutional and it uses GRU module. GRU means gated recurrent unit, which means that it consists of a gating mechanism. That is, it has like two gates, that is reset gate and update gate. Reset gate means it determines whether the previous particular information needs to be remembered or removed, and the update gate determines that whether the information needs to be updated or not. So finally, the hidden state, it updates it according to the gates, and then this hidden state is used for the GRU mechanism. So this is the architecture of Wav2Vec. For training for a process, we in Wav2Vec, it collects negative samples randomly from the entire audio sequence, and the number of negative sample is represented by lambda. And for selecting the negative sample, we select it from the same mini batch in the sense like For example, a folder containing same like several numbers of audio, but there can be many folders of similar manner. So that is same mini batch. So within the same mini batch, there can be several audios and audio examples, and within the same audio, there can be like different variations in characteristics of the audio. So, so there are two processes. Either we select different examples from the same mini batch, or we select the same sequence of audio, and we select random samples from the same sequence of audio. So in Wav2Vec, we use the combination of these two processes, where either we select negative samples from other examples, so that we can focus, the model can focus on learning the representation of the identity of the speaker. And if we draw negative samples from same sequence of audio from different points, then the model will learn about the phonic information, the pitch, and other features. So there's something called contrastive loss. Like for training, we have to reduce the loss. So the concept is that if there are two forms of positive samples, so the distance between them should be closer, and the two negative samples, the distance between them should be larger. Excuse me. So this distance, if it stays in this form, then it is yeah. So this distance, if it stays in this form, then the loss is reduced or minimized. And if this distance is more, then the loss is increased. Now we come to transformer architecture. So in the transformer architecture, the input goes into the transformer, and then we know that a transformer helps in generating the output. So So the basic architecture of the transformer is where there are several encoder stacks and several decoder stacks. So when the input is passed to the encoder stack, the input of the previous encoder is passed through the other parts of the encoder, and finally the output which comes from the last encoder is taken as the input of the decoder, and as well as the decoder also take the previous decoder layer's inputs and then generates the output. So coming to the encoder workflow. So in this, the input first passes into the as the input embeddings, and then it goes to the positional encoding, and there are stack of layers of encoders. So how input embedding works is that, for example, given a sentence, "How are you?" How it is first tokenized into each word, and these words are converted into vectors of 512 size. So these vectors like these words are converted into vectors using the input embedding, and then finally each word needs to be represented based on its position. So, for example, "How are you" should be represented one after the other. You cannot interchange the words. So to understand the position, sine waves and cos waves are used, because sine waves and cos waves will determine how close each words are from each other. So then this particular word vector and the positional encoding, which we obtain from these waves, are added together to get the embeddings for the position. Finally, this like context, positional context, is passed through the stack of encoders. So the first stack is the multi-head attention. So in multi-head attention, for example, if given a sentence, "How are you?" It tries to understand the correlation between each word of the sentence, "how," "are," and "you." So that is the task of multi-head attention. So there are three vectors. First is the query vector, which will give the representation of a specific word or token from the sequence. Then the key vector, which will give the vector for the corresponding token, and value vector is associated with each key used to construct the output of the attention layer. When a query and a key vector is multiplied, then it will give a attention score to understand that how much emphasis of that particular word should be given to a sentence. So when this query and key is passed, a linear transformation is taken, and then a matrix multiplication happens, and the process continues. So in higher dimensional data, this entire process will continue h times. So that's why it is known as multi-head attention. So we are continuing this entire process and dividing it into h times and iterating over and over again. So now the matrix multiplication of the data happens like the queries and key scores are multiplied together. We get this final score, and here it shows that how relevant, as I said, each word is with respect to other words. So this is the matrix score, and we have to scale this matrix score down. For that, we divide it by square root of the dimension of query and key vectors, and the final scaled matrix is formed. This final scale matrix passes into softmax because softmax will scale it down into zeros and ones, and the higher scores will get more higher and the lower scores will get depressed. So the attention weight is then multiplied with the value weight to get the final output. So this is how this multi-head attention works. And after the multi-head attention, it goes through the normalization part. So in normalization, there's a ReLU layer in between two linear transformation layers. So the ReLU layer will just remove the vanishing gradient problem and will try to improve the like accuracy of the output, and like it will also like remove the negative part of the data so that no too much negative forms are present. And then finally we come to the decoder workflow. So in the decoder also, the first part is almost similar to the encoder, the like output embedding, positional encodings and so on. So then after the first part, after the positional encoding, we do the multi-mask head attention. So in this, what happens that same scores code matrix is added with a, head mask, look ahead mask. So this look ahead mask will will try to, for example, if you are generating a sentence, how are you, where R will depend on previous like token, not on the future token, because we do not know the future token. So it will try to remove those future token dependencies and then get the mask score finally. And in this like in decoder, what happens that the encoder's query and key is taken, and it same working happens same in the same way. It's just that the query and key comes from the encoder and the value is from the decoder's multi-headed like matrix. So finally, after the like similar kind of working, we get the matrix that we have, and in this matrix it passes through the linear transformation, and then there is a vocabulary of like several words. So what softmax does is it gives us the probability of that how much this particular words from this particular vocabulary will be present, should be generated, like based on the matrix that we have obtained, and it will try to see that which words from the vocabulary should be present, and that particular probability is given, and the highest probability of generation is gives the generated outputs. So this decoder stack also runs several times, as I said, like both encoder and decoder stacks runs n times, and then finally the generated probabilities of outputs are obtained. So how GPT-3 model works is that it works similar to the transformer model. It's just that it is trained on higher like number of data, and it also extracts the key ideas, context, tones, and meanings from the unstructured data. And it has, as I said, it has 175 billion parameters. So it has a large number of parameters, and it needs a large number of space to be trained. The two key features of GPT is preset and temperature. Preset is the prompt that we give to the model, whether to generate chat response or to summarize a text or to translate the language. And temperature is the setting that will control the creativity of the model during the text generation. So lower the temperature, it results to lesser creative output. and higher the temperature, it will result to higher creative output. So now we come to the signal processing of the audio. Actually, we need the signal processing of the audio. As I said, in contrastive predictive coding, we pass a particular vector called x. So before passing that vector, to obtain that vector, we need the signal processing and a logic called Fourier transform. So signal is basically a variation of any quantity over time, and in this is a waveform. So in this waveform, we will try to see the variation of amplitude over time. So that is a signal, and then we try to extract meaningful information from this waveform using a technique called Fourier transform. So in Fourier transform, an audio signal which is comprised of several frequencies, a single frequency is taken over time, and we only capture the resulting amplitudes. So the Fourier transform is a mathematical formula which will allow us to decompose this signal into individual frequencies and frequency amplitudes. So in other words, it will convert the signals from the time domain into the frequency domain, and the result that we obtain is known as spectrum. So to understand how to convert from time domain to frequency domain, uh, this is possible. Like for example, we have this kind of periodic graph. So y equal to ft. In this, the time period is 2 pi. That means the period between them is 2 pi. So uh, the frequency is 1 by 2 pi here, and it can be denoted in the form of this function in the form of cos and sine, where my a0 is the baseline function which can be shifted up and down, and its average value of the function over time for a period. And this why do we use cos and sine? Because cos and sine is also a periodic function, and secondly, it is easy to differentiate when we use cos and sine in the equation. And a1, b1, these are the weights which will tell how much cos and sine function is involved within this equation. So this series is known as Fourier series, and the best part of this series is that the weights a1, a2, and these weights are will give us how much each frequency signal is present in the entire audio. So if a1 is say greater than a2, that means that because a1 is of time period 2 pi and a2 is of time period pi, so that means the frequency of 1 by 2 pi is more present than the frequency of 1 by pi. So now the concept of Fourier transform has to be explained. For example, there is one pure form of frequency that is of 450 beats per second, which is known as A note, and the other form of frequency, which is D note, which is 270 beats per second. So when we combine these two forms, so it's almost like this displacement and this displacement is combined together. So we get this displacement finally. So this is the combined form of frequency. And similarly, when we combine several kind of frequency, we get this graph. And to get a Fourier transform, first what we do is consider an intensity. This is a graph where we have 3 beats per second, and we just take this graph and rotate it, or like wound it over a circle. So the vector here, this is a rotating vector. Say, for example, if given a name, this is a rotating vector v. So this rotates over entire graph, and at the highest point of the graph, it is closer, it is farther from the origin, and the lowest point is closer to the origin. So this graph has different, this graph is near about 0.5 beats per cycle. It is calculated based on each cycle, and this is calculated based on beats per second. So what we do is when the rotating vector keeps oscillating in this particular graph in a higher speed, slowly it it becomes like this oscillation becomes such that when it matches this 3 cycles per second and this 3 beats per second, when the matching happens, the graph looks somewhat like this. So in this graph, you can see that all the points which are positive, like all the higher points are present here, and all the points which are negative are present here. And the center of mass is at this position. So when the matching of beats had not happened, the center of mass was almost close to the origin. And finally, when the matching had happened, the center of mass shifted towards the left. So our task is to plot this particular center of mass and how it moves over as the rotating vector keeps moving. So when we plot the center of mass, it is shown that initially it was really at a higher position because we didn't have any waveform. And then as the waveform started oscillating, like the vector started oscillating, so the center of mass remained towards the origin. And then finally at 3 beats per second, there was a peak found. And this peak will help us to understand that what kind of pitch is formed in the particular graph. So similarly, if we combine two kind of graph, as I said, 2 hertz and 3 hertz frequency graphs, so then what will happen? There will be two peaks found at 2 hertz and 3 hertz. So similarly, this way we can understand the major information. We can pick up the pitch information easily from this particular graph of center of mass. So almost Fourier transform is something which will actually change the this frequency graph into the graph of the center of mass, so that we can understand. We do not need these kind of like these waveforms are not needed anymore, and we just know the exactly the waveform which is in the information which is needed for us. So finally, for this is like if for 2 hertz frequency, for 3 hertz frequency, and this is the graph for both, combination of both. And when we do almost Fourier transform, we can see that it's the sum of these two itself. So the calculation, how it happens is that, as I said, we wound it around a circle, and when in a if we have a rotating vector in a circle, so the formula is like e to the power 2 pi I into t. This is the Euler's formula. So in this Euler's formula, this 2 pi is the perimeter of the circle, and t is the time. So when this vector keeps rotating, so it also depends on the like kind of rotation. So if it is rotating clockwise, then it will be positive, and if it is rotating anti-clockwise, then we have to put a negative sign in here. So and we also add the frequency because our major aim is to calculate the frequency itself. And so what do we do is, given a graph GT, we put points around this graph, like infinite number of points, so that the entire graph is denoted by points. And then we wound that around the circle so that we get this formula from the Euler's formula that was obtained before. That is GT into e to the power minus 2 pi I ft. So why are we doing integration? Because we are using, like, within this particular time period, we are using this waveform. So and there are several like infinite number of points in there. So we have to integrate that. And similarly, if we do the same thing for the entire audio waveform, so we integrate it from minus infinity to plus infinity. So this is the Euler, this is the Fourier transform formula. And then there's something called spectrogram. One more thing, Fourier transform is calculated by the algorithm called fast Fourier transform. And in a spectrogram is basically like Fourier transform is used only when the signals are periodic. So it's not possible that sometimes the signals are not periodic in the input signal. So for non-periodic signals, we have to divide the signal into small loops or windows, we say this. And these window segments, for each window segments, the Fourier transform is calculated, and overlapping all these Fourier transforms outputs generates a particular spectrogram. So that is the concept of spectrogram. So the spectrogram will look something like this. This is the frequency at the y-axis and the time at the x-axis. And then we have various like based on the level of pitch, we have this color encoding. And another thing that we use a different kind of scale, like instead of the like general scale, we use a smell scale. Why do we use that? Because our normal ears cannot understand the difference between certain frequencies. For example, if we have frequency difference of 500 hertz and 1000 hertz, that is easy to understand by hearing. But if we have 10,000 to 10,500, even though the difference is same, but we cannot hear that sound. So we change it into a mel scale, so that it's easier for us to perform the computations and here differentiate between the similar kind of units. So the graph again looks same as the spectrogram graph, because this is a mel space spectrogram. It's basically the same thing where the entire frequency after calculation, it is converted into the mel unit, and then it is plotted in the spectrogram graph. So it looks same. And now we'll come to CNN. So um, these are the these are path by path explanation of each part of the architecture that will go into the whisper. So CNN, I think everybody knows CNN is the convolutional neural networks, where it helps us to break down a particular image and to understand all the features of the image, and then to identify what kind of image it is. So CNN works as that, for example, this is a koala bear's image. So we have all the features in here. So all the features combined together, it will give the head, and the hands and legs combined together, it will give the body, and then finally it will denote whether it's what kind of image it is. So similarly, if we try to find for a digits image, we have this head of the digit, and we have this the between part, and then the diagonal part. So these are denoted by matrices, and these matrices are called filters. So the calculations happens as that in a particular image, we take we traverse 3 cross 3 matrix. So the first 3 cross 3 matrix is taken, multiplied with the filter. So this is the filter for the head. So first 3 cross 3 matrix multiplied with the filter, and then divided by the number of numbers present here, and then we get the feature map. So similarly, this 3 cross 3 matrix is shifted from here. So this is taken and then multiplied, and all over the image it is shifted, and we get the final feature map here. So here you see in the feature map also, mostly the values are negative. Only the position where the head of 9 was present, that position the value is 1. So that denotes that at this position the 9 head was present. So similarly, we have various other filters also for denoting this part, for denoting the diagonal part, and all the filters together multiplied with the image, we get various feature maps. So for this particular image also, we have different features, and we have the filters, and we have the outputs coming out, and then we denote head. For head and body also, again, we have the filters multiplied with it and the feature maps. And then finally, we flatten this array, and this flattened array goes through a dense neural network. Why do we use this dense neural network? Is that we have to classify a particular image, whether this image is if the position of that particular koala bear has changed or not. So we have to classify that. So that's why this flattened image is then passes through various other images of the koala bear, so that we can understand based on the position different kinds of images. So see, if the image changes, the position changes, so then again the neural networks can work in the same way. So now this feature map also needs to, there are several negative values here. So we kind of do not need these negative values. So it passes through a ReLU activation function, so that the negative values is changed into zeros. And again, in this part also, there are a lot of zeros, right? So it becomes kind of a sparse matrix, and the dimension is also too high, just processing zeros. So we use something called max pooling. So what it does is it takes maximum from a part of the matrix. So if we take this 4 cross 4, like 2 cross 2 matrix, so from this 4 numbers, the maximum is 1. So we put 1 here. Similarly, from this 4 number, the maximum is 0.33, and so on. So the benefits of pooling is that it reduces the dimensions and computation, and also overfitting. And the model also can understand various locations of the particular image. So it is location invariant. It does not. It does not, like the model does not. Uh, Model can differentiate between the image's location, and can give a proper output. And this is the final architecture of the convolutional layers, where we have various convolutional layers and the ReLU. And then we have, and these are the features. So then we have the pooling. Then again, when we have head and body detected, we again go through the various convolutional layer plus ReLU. Then the pooling happens, and then finally the flattened output is generated. So for the audio also, there are various features present. See, it's almost like images, that when in images also, in CNN we use certain features. So audios also has features, like previously I explained MEL spectrogram. So that is one of the feature. So the MEL spectrogram converts this audio also in somewhat 2D form, where it's kind of a heat map, where my x-axis is denoted by time, and y-axis is represented by frequencies, and each color intensity represents the magnitude of a corresponding frequency. So and there's some other features also in audio, such as chromogram feature, which is an image like features which will distinguish between various pitch classes, and maps them to the audio. So these kind of features are used, and the CNN works similarly as it works in images. But as it was pretty difficult to show in form of audio, so images was easier to show. So the workflow is same. It's just that the feature passes through it and determines that which kind of audio it is. And uh, there's something called ReLU activation function. So as I talked about ReLU activation function, so it's actually a combination of ReLU activation function and a dropout function. So dropout is basically we randomly drop certain neurons from the hidden layers, so that when the neural network works, it does not focus on a specific neuron, or the bias does not comes into picture. So in KLU, what happens, the weighted sum of the input features is multiplied with the cumulative distribution function. And the cumulative distribution function has a normal distribution. So here we have, for example, for an input feature, this input feature, each parts of the input feature follows a normal distribution. And therefore we know that the normal distribution have PDF, this the PDF of normal distribution, and under mu 0 and standard deviation 1, the PDF changes this way. So in GELU, it will map the negative inputs to 0 and the positive input to the input itself. So what it does is that for larger values of x, it should be multiplied with 1, and for specific values of x, it should be presented in equal, less than or equal to a specific value. So this is the given formula, and the area, this is the area under curve, which is shown for specific x values. So given this formula, we try to use like the GELU activation function works almost like this. We multiply it with the phi formula, and integration is done because of the, if the distribution is continuous. If the distribution is discrete, then we just add up the probabilities. So then we find out the Gauss error function, and we try to we find out the Gauss error function and try to get it in the form of phi. And after that, the GELU function somewhat looks like this. Along with the, we can also represent it in terms of tan H and sigmoid, which is a easier representation. So then there's something called sensorial positional encoding, which is mainly used in terms of audios. it uses sensible functions with different frequencies to encode the position of each element in the sequence. So it uses the sine and cosine function itself, and which is used to represent the even and odd positions in a audio frequency sequence. So this method is based on the idea that the position of the token can be represented as a series of sine and cos frequencies, where each frequency corresponds to different position in the sequence. So the sine and cos functions are chosen because they are cyclic in nature, and it allows us to return the information about the position of a token, and in a way that it is easy for the model to learn. And the position encoding is calculated using geometric progression frequencies, where frequencies of sine and cos functions increase potentially, and exponentially it increases here, and as the position of the sequence increases. So why do we use the denominator as 10,000? Is that in the encoding, the transformer model is related to the wavelength of the sensorial function, and the wavelength is a geometric progression which is between 2 pi to 10,000 into 2 pi. So that's why we use this 10,000 as a denominator, which means that the difference between the peaks of the sensorial function increases exponentially as the position in the sequence increases. So this is the formula to calculate for each sine and cos waves, the odd position and the even position of the wavelength of a particular frequency. So then we come to perceptron. So perceptron is basically given an input, there are certain weights we try to find out the output. It has only like one kind of layer. So we calculate the dot product of the weights and the inputs, and then finally we get the output. So this is a step function in between, which kind of makes a threshold that, for example, if the output that we have obtained is less than that particular threshold, then we generate output as 0, and otherwise we get output as 1. So this is the function of this this step function. And the update rule of weights is the new weight is equals to the old weight plus learning rate minus the previous predicted output and the output that is given, so into the inputs. So this is the update rule, and we also add a bias to it so that we can calculate the output finally. So the multi-layer perceptron is basically the combination of several perceptrons together. So for example, for this particular graph, classifying into different points is difficult. We need this kind of boundary. So what multi-layer perceptron does is, for a single perceptron, we can have one boundary, and for another perceptron, we can have different boundary. Adding them together, a boundary like this is created, and we can smoothen it out to get a final boundary. So that means a combination of various perceptron gives a single multi-layer perceptron. So this is the combination here. The like data set of CGP and IQ is taken, where we have weights and biases, and we are trying to combine this one perceptron of six bias and another perceptron of three bias to get the final output. So now we come to the Whisper architecture. So the Whisper architecture actually works. This part is actually the comes from the previous token after we get, like after we end, and this again it starts over all over again. So actually it starts from the start of transcription. So after starting the transcription, there is a language tag that should be present, and no speech in the sense, for example, if there is music and there's no voice in it. So if there is no speech, then it directly ends the operation. And if there is a given language tag to be transcribed or translated to, so there will be two tasks: transcription and translation. So transcription can be from one particular language to any other languages, and translation is only in English language. So after that, uh, there like the generation can be such that if given a time frame, So it can generate based on the time frame. It can begin the time, generate one token, end the time, and then repeatedly work that way. And if there's no time frame given, it can just generate the tokens directly. So this is how the multitasking format of the Whisper architecture works. So this particular like format is actually passed in the Whisper architecture here. So the architecture is such that first the audio is converted into a log-mel spectrogram, as I explained before, and then we use the convolutional layer plus GALU. So there are two convolutional layers and GALU. Finally, the vector that is obtained goes through a sensitive positional encoding. So sensitive positional encoding will like give a position of each frequency, odd and even frequencies, and then it goes through the like block of encoders. So the encoders generally consist of self attention and cross attention layers. So in encoder we have self attention, and in decoder we have cross attention layers. So what is the difference between self and cross attention is that in self attention layer like we directly use the query vector and the key vector as well as the value vector from the encoder itself. And in cross attention layer, we use the query vectors, and the value vector comes from the target sequence, and the key vector comes from the encoder output. So the final encoder output will give the key vector, and the target sequence will give the query and the like value vector that is coming from the decoder. So that is the difference between cross and self attention. Cross attention will use both the like input and output from decoder and encoder. Self will just use from encoder itself. So and then there are multi-layer perceptron in between. So finally, the output from the encoder generated goes through the decoder using the cross attention mechanism. And here also we have only three layers: self attention, cross attention, and multi layer perceptron. And this repetition of the decoder and encoder happens simultaneously. And then finally we get the prediction. So as I said, the multitasking format is passed in the decoder, and in that format itself the prediction is obtained. So the this is a format I have explained before, and this format is again like English is the generated output language, the transcription task. This is the time frame, and this is the generate output. That's it for the presentation. Thank you. Any questions?
Thanks, Ritvika. A really nice presentation. I do have a question. So, this is back to where you have mentioned this particular bit of language detection within Whisper, right? So
Yeah.
I think they are including a token just to hint it out. Ki, okay, this is the language that the audio is coming in, so that the model can actually be conditioned on it. So, what are they doing? Like, how are they estimating or predicting that particular token? Have they given any mechanisms to do that in the paper?
The tokens that the audio is coming in no, actually first they are converting the audio into the log-mel spectrogram, as I said. So when they convert the audio into the log-mel spectrogram, so it automatically forms into a vector. So that particular vector itself goes into the encoder layers.
Right. So in the decoder you have mentioned, like the entire there in the input to the decoder, they
Huh.
have different tokens, right? One of the tokens is start of transcription or start of sequence token, and then they also have a language detection token, right?
Yeah, yeah.
Language identifier. That how are they giving that identifier?
Can
They
you present sorry, Ritika, can you present the slide once more?
yeah,
I
yeah.
think
I got
it
the
is,
question.
yeah, in the first slide, I think Abhishek is talking about.
I think this is the
Yeah, so I'm
Just the
talking about
first
this
slide.
because this is the same problem even that we were facing, right?
uh,
Ritika, you were creating that classifier to tell the indic trans, the
this
indic Wav2Vec.
multitasking format you're talking about, right? In
Ah,
the
right, right. So they have this not, where is that? Language tag. Yes. So how
yeah,
are they giving this language tag?
this
Have they
is
written anything in the paper?
no, this is taken actually as an input. from the user itself, either as an input or given an option for which particular language you want it to be transcribed in.
Oh, okay, okay.
Yeah.
So, but how is Whisper then working for us? Like we tried Whisper, right? So we didn't have to give it any sort of language tag
No,
in the beginning.
we had
We
to give
had to.
it
Okay.
in, yeah, we had
Okay,
to
okay.
give a particular, like inside the function itself, there's a
Hmm.
parameter of giving languages. So we had
Hmm.
to give en as English, we had to give hn as Hindi. So
Acha. Okay, okay,
yeah.
okay. So then it makes sense to even for us to create a classifier for the languages, right? Because if all these models do require some sort of hint around it, I think, and if you want to have this conversation around different languages, then to automate it, we might have to create a classifier. That's the only thing.
Yeah, that's what previously I had created. I was using Whisper. I switched to Indic Wav2Vec because of that reason itself. Because then I like manually created the classify thing using a model and then passing that to the input. We can do this like that creating of classifier. We can do here also, like if we use a different, yeah, then we have to use a different model architecture, and then again that model architecture will classify that particular audio, and that classification can be passed as a language tag here, so
Hmm.
that can
Right, right. So the only good thing with Whisper is then it's a unified model for all languages. We don't have to like keep on swapping different models like what we were doing with Indic Wave to
be,
Vec,
yeah,
right?
that's the good.
That's the only good thing, right? Okay.
Yeah, so I also wanted to understand this particular slide a bit more. So here, the input will be in any language, any audio you're saying, right?
Yeah,
And the language tag is like identifying which, suppose I'm inputting it in English or Hindi, the language tag will denote the what is the language I'm inputting in.
yeah.
And so there's a transcribe tag as well, is it? Or does it transcribe to what, any language or
Even
uh,
in transcribe function we have to give the particular transcription language, otherwise it will always transcribe in English only.
Acha, so we can transcribe or translate to any other language that we need, and then it will go to the next person.
Yeah.
Then. Okay.